And can I just get a thumbs up to confirm that that everyone's able to see my screen? Okay, great. So for today, we're going to be talking about kind of like the fundamentals of heat pumps, and this is really going to be through the lens of being in Massachusetts and having a really great utility program. So we're really, hopefully by the end of today's session, you'll kind of get an idea of like heat pump sizing, capacity, what the operating costs could look like. So it's really kind of just this high level, like just realizing where they fit in the Massachusetts marketplace in terms of like HVAC equipment. And hopefully you'll have a pretty good understanding of what they can and can't do, and how that's informed by like sizing and design. We're also going to be covering ground source heat pumps briefly, as well as air to water heat pumps. But a good chunk of this will be going over just kind of like what this equipment can look like inside of homes and how it works. All right. So a few just big picture comments is that we need to dramatically lower the amount of carbon being released into the atmosphere, and in our built environment is about 25% of all the emissions that's going into the atmosphere. So it's just like with transportation, there's like a huge opportunity to be lowering carbon emissions through electrification. Another thing that I will say is that energy efficiency improvements impactfully change the way a home performs. So that goes in two directions in terms of heat pumps. Like one, a tighter home, a more energy efficient home is going to be a cheaper home to operate. So we always want to be bringing down the load because it lowers the amount of energy consumption in a home. And lowering energy consumption means lowering operating costs. And traditionally, operating cost or savings has always been kind of a big driver in terms of like energy efficiency in making these types of programs work. Another thing that is important with this comment is you got to size the heat pump system for the home. And if you're not doing it for the home, you're going to end up with an oversized system that's going to be more expensive to operate, or an undersized system that isn't going to be keeping up. So it is really important to be sizing the heat pump system based off of the energy efficiency improvements that someone may be able to make. Another core concepts over here is that this technology is new. Cold climate air source heat pumps without a capacity drop weren't a real product category a few years ago. So part of this big picture and part of this training is just highlighting that this equipment is available, and also being able to distinguish that not all heat pumps and not all cold climate heat pumps may be the right selection or the right choice for a customer. So making sure that the product being selected is the appropriate one for the home. And then the last kind of big picture thing is that heat pumps that are well installed and well designed can have a dramatic improvement of the comfort of a home. Alternatively, say, a poorly designed heat pump system could make the home significantly more uncomfortable, or it could be that changing over from an old steam boiler over to a heat pump may make the basement really cold. So it's just also being aware of like that we're going to be fundamentally changing the way that homes are performing, and comfort is something that needs to be acknowledged when making that switch. All right, so what is a heat pump? So a heat pump is an electrical device. There's no combustion taking place, and it moves energy from one location over to another. So in the wintertime, it's moving energy from the outside air, and it dumps that energy into the home in the form of heat. And in the summertime, a heat pump takes heat as well as moisture from inside that home, and it dumps it to the outside. So fundamentally, all a heat pump is an electric device that moves energy from point A to point B. Other core concepts with heat pumps is that for some people in some regions that there's real savings compared to oil and propane. In other regions or in other parts of the state, there could even be some savings compared to natural gas. However, in other parts of the state, it could be that heat pumps could be about 2x more expensive to run than a gas-fired system. With heat pumps, not only does it move heat, or not only can they add heat, but they can also remove heat in the summertime. And do know that heat pumps are about 2x more efficient as a cooling system than a window air conditioner or a old central AC. And then the other thing too is that it's like modulating inverter driven variable speed. It is like all of the latest and greatest HVAC technology to be improving comfort if the system is well designed. So there's a real opportunity that your heat pump system is going to be significantly more comfortable than a traditional fossil fuel fired furnace or a single stage central AC. I wanted to highlight this article. It came out about 1.5 years ago and is from the Boston Globe, and it's just about where Massachusetts is in terms of heat pump adoption. And it was just saying, oh, Massachusetts is far behind, but things are certainly going better, especially with towns that did heat smart campaigns, which really helped the uptick on adoption. But I want to highlight a few quotes over here. So like, this is still true in the Massachusetts marketplace for the most part. But it highlights some of the facts that like heat pump adoption is not always going to be easy. And some of the reasons it's not easy is because of the contractor marketplace. So one quote from the Globe article that I thought was interesting is that some homeowners said contractors affiliated with Mass Save dissuaded them from removing their fossil fuel-based systems and going all electric. Another good quote on here was some residents said that they sought to convert their homes off of fossil fuels. Contractors, including those associated with Mass Save's energy audit program, told them that heat pumps alone could not heat a home adequately throughout a Massachusetts winter. And the last one that I'll quote is, out of the 5 contractors he spoke with, only one was fully comfortable fully converting his oil burning heating system to heat pumps. And what I think about this article is that like the marketplace still has some ways to go. So nothing changed radically overnight from like 1.5 years ago to today. Most of the times, if you're, let's say, just trying to get 5 quotes for heat pumps, you're probably not going to get 5 perfectly designed whole home heat pump systems. You're probably going to get some misinformation. So part of the reason why we're doing this training is to really just like understand like what is a home's load, how to size a heat pump system to meet it. And if you do those things, there's really nothing to worry about with the equipment not being able to keep up. So hopefully by the end of today, you'll feel like all of these comments shouldn't be actively happening anymore. All right, so we're gonna start getting a little technical here. So with this slide, we have 3 different houses. So we have an old leaky farmhouse, we have like a post-World War II Cape, and then we have a home that looks somewhat high-ish performance. Each of these different homes is going to require a different amount of energy to be added into the home when it's 5 degrees outside to be able to maintain 70 degrees inside. So let's say that the house on the left-hand side, there's going to be energy leaking out from like the windows, the walls, the ceilings, the doors through air infiltration, air exfiltration. It's going to have energy leaving the house through all of those components. And to be able to maintain, say, 70 degrees inside, this home is going to need around 100,000 BTUs, which are called British thermal units. And that's the metric that, that's the unit that all HVAC equipment uses to measure its heating capacity. So the leaky old farmhouse is going to need 100,000 British thermal units every single hour when it's 5 degrees outside to be able to maintain 70 degrees. Say the smaller Cape, which is also newer and likely has some insulation throughout it, that home's going to need probably somewhere around 50,000 BTUs per hour. And the home that looks high-ish performance is going to need around 24,000 BTUs per hour. So we have 3 different homes, 3 different heat loads. Now, on the bottom, I have 2 pieces of equipment, and both of the pieces of equipment are from Mitsubishi. But I could have pulled equipment from like Fujitsu or LG or Daikin or Bosch or Carrier or York or Trane or Goodman. Like there's lots of different heat pump manufacturers. So don't think that just because I'm highlighting Mitsubishi equipment over here, don't think that it's the only solution. There's 2 different heat pumps that I'm showing off. So one is on the left-hand side, and this heat pump on the left-hand side, when it's 47 degrees outside, is 30,000 BTUs. But when this is at 5 degrees outside, this heat pump only has 12,000 BTUs. So say I took this heat pump and I put it in the leaky old farmhouse. I would need 9 of this piece of equipment, this outdoor piece of equipment, to be able to fully heat the house when it's 5 degrees outside. Say that I took this Cape Cod style home. I would need 4 or 5 of this heat pump to be able to fully heat that home. And say if I had that high performance home, I would need 2 of this outdoor unit to fully heat the home. If instead of, say, putting in this standard mini split style heat pump, instead I put in the hyper heat system. And like all of those manufacturers that I rattled down earlier, like they all have somewhat of an equivalent of this type of technology. And what this technology is whether it's 47 degrees outside or whether it's 5 degrees outside, this heat pump still has 30,000 BTUs worth of heating capacity. So if I had the leaky old farmhouse, I could put in 3 or 4 of this style heat pump and fully heat that home. Say if I had the Cape Cod style home, I could just put in 2 of this heat pump system and fully heat that home. And say if I had the high performance home, I could put in 1 of this heat pump and fully heat that home. So it's never that heat pumps are wrong or heat pumps are right. It's figuring out the load of the home and selecting the right equipment to meet 100% of that building's heat load. We'll talk about sub-zero temperatures eventually, but do know with the heat pump system for all of Eastern Massachusetts, the design temperatures are all above freezing. So this type of equipment is really, really appropriate for our region. So I was talking to Joe earlier today about decarbonizing 100-year-old homes. And that's what we have right over here, which is my home. So my home, when I bought it, well, it still is, it's a 4-square colonial. It was built in 1909. When I bought the home, there was no insulation in the walls, single pane windows. It was really leaky. It's still a little leaky. Not having a well-defined thermal envelope. It was like an old leaky home, like a lot of homes in like Melrose and Natick. And Concord has a lot of old homes as well. But this is what the home looks like. And then down in the basement was a steam heating system. Okay. And when I go and I looked at the label of the steam heating system that was down in the basement, what I would find was a heating system that could put out 129,000 BTUs per hour. So let's just say I have this steam heating system that could power this old leaky farmhouse. This old leaky farmhouse needed 100,000 BTUs. This steam heating system put out 129,000 BTUs. So the heating system had more capacity than the home would need. When I bought my house, one of the things that I did is I did an accurate heat load calculation. And what that means is that you have a modeling software and you put in information about the home, the square footage of the floor, the square footage of the ceiling, the walls, the windows, how leaky the home is, the type of insulation in the walls, the type of glazing on the windows, the type of insulation in the attic. And when you put in all of the inputs, what will happen is you'll generate a heat load calculation, and that's referred to as the manual J report. And what this does is it says, hey, this home needs 108,000 BTUs per hour. And if I were to like look at the report a little bit closer, I could see kind of where the modeling software is predicting kind of all of the energy losses happening.
Excuse me, Mike.
Yeah.
It's Joe. I have a quick question, if you don't mind. Is
Yep.
the indication of the BTU hour capacity of a boiler a standard feature on its label?
You got it. Yeah. Sometimes there'll be two different numbers. There'll be like a max and a min, and the difference between the two, or an input and an output, is between it would be the efficiency of the boiler. So sometimes you'll see like if you open it up and you look at the label, you'll see like 100,000 BTUs input and 80,000 BTUs output, and that would be because the boiler is 80% efficient. But yeah, all heating systems, you can, if you go and look at the label, you'll see what the size of that system is. One thing that could be a follow-up comment over here is you should never size the heat pump system based off of the capacity of the existing equipment that's down in the basement or in the utility room, just because it very well may have not been properly sized the first time. And as we're about to see, the performance of a home can change as well. Did that answer your question, Joe? Okay. So say for my own home, I didn't leave the conditions of the home as is. One of the things that I did is I took full advantage of the Mass Save program. If I was in Concord or Reading Municipal Light Department, I would also be taking full advantage of their own weatherization programs. But some of the improvements that I made were I packed the walls full of insulation. I fixed the attic. I had the house professionally air sealed, and I also upgraded all of my windows except for architecturally important ones. And what ended up happening after I made all of those improvements is when I reran the Manual J software, the heating load calculation software, instead of having a home that needed over 100,000 BTUs, I ended up having a home that needed just shy of 48,000 BTUs. And say if I were to go and look for heat pump equipment, I would find that they make heat pump systems that when it's 5 degrees outside, this heat pump can provide 54,000 BTUs per hour. So I could just put in one outdoor system and then tie that to, say, multiple indoor units. One of the benefits of weatherizing the home and buttoning it up versus sizing the heat pump system for 100,000 BTUs would be this. One, when you drop the heat load in half, it cuts your annual operating cost in half. Another big thing that's exciting is instead of the heat pump system costing around $50,000 to install, it brought it down to just shy of 25. And the other thing that's worth noting, and we'll talk more about electrical and amps and electrical service and main electrical panel a little bit later on in training, but we need to decarbonize, or we need to electrify everything, including like domestic hot water, cooking, transportation, and all of those things require real electrical capacity. And just putting in, say, another very large heat pump system is likely going to prevent me from electrifying other things that I may want to in the future, like getting a fast, like a level 2 EV charger, putting in a solar thermal hot water system. So by reducing the load in the home, it frees up around an additional 30 amps of electrical service that I could be using for other things as well. So this reduction may be preventing me from needing to spend $5,000 in the future for improving the electrical service coming into my home. Any questions with anything that we just covered on the first section?
Yes, it's Joe again.
I know.
When we tighten up the home with insulation and air sealing, is there a concern with radon in this region?
Yeah, Massachusetts has higher radon levels than other parts of the country. So a few things. So one thing that there's been multiple studies about this. So radon doesn't seep out of the foundation. It more or less gets pulled out of the foundation. It gets pulled out of the foundation because, say, in the winter time, we're warming up the air in the house. We're making it warm and buoyant so it rises up and out. And because of that, it causes negative pressure or suction down below. So if you live in a 2-story home right now and you like open the windows on the second floor and you open the windows on the first floor windows would feel wicked drafty, and the second floor windows would be like, oh, it's not that bad of a day outside, because on the second floor would be all the air exfiltrating from the house. So do know when you tighten up a home, one of the things that you're doing is like, yes, you could be trapping more radon in the home, but at the same time, you're preventing less negative pressure or less suction of the radioactive gas from coming up through the basement. So with the case studies that I've seen, air sealing and weatherizing a home doesn't lead to any higher radon concentrations. But at the same time, radon testing is wicked cheap. And the abatement of it's not that expensive. So I'm not going to try to confuse this and be like, oh, don't worry about it. Like, yes, you should definitely worry about radioactive gas leaking out of your basement, but it shouldn't be like, oh, should I be living with radioactive gas or should I be weatherizing my home? Like, those two things are somewhat siloed in my opinion. So hopefully that helps.
So do you recommend radon testing prior to or after the weatherization?
So with radon testing, I would do it after the weatherization, but also with radon testing, doing it over the course of multiple seasons can also be helpful as well. Because there's lots. So do you know that like the radon test kits, the like one time put them in the basement, leave them there for a month, send them in the mail? They're like $5 a piece, so it's not that expensive to be doing for testing for radon. But I would recommend doing it more than just one season, just because it could be performing differently as soil conditions change throughout the year.
Mike, I had a question for you.
Yep.
Jillian. So I'm selfishly interested in this course also because I'm trying to get heat pumps at my house. My house was built in the 60s and it's new to me, but it has it has baseboard heating and no air conditioning. And so air conditioning is kind of a main motivator, like in terms of comfort for us. It has a really new oil heater, unfortunately. So anyway, one thing we did is one of the first things we did was do tons of mass save insulation like you did for your house. And now we've started talking to heat pump installers and they're telling us that we should have talked to them first because now we've added insulation to our attic and that will make it harder for us to install like maybe a centralized system that is ducted to the bedrooms upstairs.
Yeah.
And I've had 2 of them, and they're ones that are from Abode's preferred list say, oh no, you should always do HVAC before insulation. And I'm like, crap, because that seems so frustrating to me that I've like somehow added cost now by doing insulation. I'm wondering, do you have guidance on that? Because I always hear you and the Mass Save people say insulation first, and I just wanted to ask about that.
Yeah, so there's no getting around the fact that it's easier to install a heat pump system without swimming across a sea of insulation. But do you know that with the insulation being up there, you push it out of the way and then you push it back afterwards. So it's not at all a deal breaker. As far as with the order of operations go, I would recommend sizing the heat pump system based off of the Mass Save recommendations. And that's really only true to like pause on the install when it is like a ducted system going in a second floor attic where insulation is going to be everywhere. Like say for putting in a ductless unit, it doesn't matter if there's insulation in the walls or not, that Mass Save had put in there, or say like inside of a basement, like even if they insulate the ceiling insulation isn't in the way. So it really is just kind of a somewhat unique one-off-ish. It's not like a perfect storm, but it really is when someone wants a ducted system in their attic and their attic is unfloored. So Mass Save just blew a lot of insulation everywhere. For the rebates, as far as Mass Save goes, you're welcome to install the heat pump system, then you can install the insulation, and then you can apply for the rebate. So it doesn't affect like rebate eligibility if you kind of like first put in heat pumps and then put in the whole, fully weatherize the home. But
So,
yeah, there
Mike,
is.
That's true. That's true for loose or celluloid or batting of type of insulation. But the foam insulation hardens in such a way that it is an impediment to ducting.
It is very, very, very uncommon to find anyone using closed or open cell spray foam on an attic floor in Massachusetts. So normally when someone's doing spray foam insulation, they're doing it along the rafters and wouldn't be doing it along the floor where it would be impacting the install.
Thank you.
Yeah. But yeah, Joe's right that if they were to be doing spray foam on the floor, it would make it a real pain in the neck. And we'll talk a little bit more about spray foam in the next session as well. All right. So with a heat pump, this is like my least favorite topic, but with explaining how they work, but I'll give it a shot. Okay. So let's just go over what's happening over here. So there's an outdoor unit, and from the outdoor unit, there's going to be refrigerant lines and electrical line running over to an indoor unit. Okay, so that's all the components. There's something inside, there's something outside, and there's something that is transferring energy as well as electricity between the two. So what's happening over here in the wintertime is this. I guess there's two important, there's at least one important equation. No, there's two important, like say thermodynamics or physics principles. So one is hot goes to cold. So hot or high concentrations of energy always go to low concentrations of energy. So you can see this with a few different examples. So say that you have a hot mug of coffee and you just leave it out. Eventually it's going to become a room temperature cup of coffee. Where did that energy go? Inside of the coffee, it went out into the room over time. So high concentrations go to low concentrations. The other principle, thermodynamic principle, is this. Delta T, so a change in temperature equals a change in pressure. So what a heat pump does, it just plays around with these two different components, okay? So let's just look at what's happening over here. So we have a unit outside, and what we want to do with it is we want to bring heat or bring energy into the house. So how we're going to do this is this. We are going to start off with making something really, really cold. And it's going to become really, really cold because they're going to be releasing all of the pressure or decreasing all of the pressure on this refrigerant. Okay, so let's just say it's 0 degrees outside. There was 0 degree refrigerant, but then they decrease the pressure and that equals decreased temperature. So now this refrigerant, instead of being 0 degrees, is going to be like -30 degrees. It's 0 degrees outside. Hot goes to cold. So it may not seem like there's a lot of energy in 0 degree air, but 0 degree air is a lot warmer than -30 degree air. So what ends up happening is We have negative 30-degree refrigerant, 0-degree air. That refrigerant over time is going to become 0-degree refrigerant. And how that ends up happening is there's a fan on this system that's blowing 0-degree air over this negative 30-degree refrigerant that's inside of a coil. The next step is this refrigerant is going to be pumped. This refrigerant is going to be pressurized. So as you increase pressure, it's going to increase temperature. And what ends up happening is when you pressurize this type of refrigerant, it's going to suddenly become 80 degrees or 100 degrees. And then that refrigerant is going to be brought to the indoor unit, where air from the home is going to take this 80 or 100-degree refrigerant and eventually make this refrigerant 70 degrees, because the inside air is taking the energy or taking the heat off of it. So now this 70-degree refrigerant goes back outside, the pressure is removed from it, it becomes negative 30 again. Then more air from the outside is blown at it, it becomes 0-degree refrigerant, they pressurize the heck out of it, and then it's going to become 80 or 100 degrees again. So that process just keeps happening over and over and over again over the course of the entire winter, and the reverse happens over the course of the entire summer. It works the same way as a refrigerator, it works the same way as a window air conditioner. And sometimes when someone asks, like, how does a heat pump work? I just say they work great, or they work better than you could ever imagine. So you don't have to get into that detailed explanation of it. And I know that it's like really confusing, but it's just a device. It's an electrical contraption. It just moves energy from location A and dumps it to location B through the refrigeration process, which has been around for over 100 years. All right. So how efficient is a heat pump? So I mentioned, I guess, like one vocab word was heat load or manual J report. The next important, I guess, vocab word will be coefficient of performance, which we refer to as the COP of the heat pump system. And this is typically how I think of the efficiency of it, as well as like the NEEP database, how they list the efficiency, but let's just go over what this means. So say you have a fossil fuel-based system. You put in, say, 1 gallon of home heating oil into this contraption that's down in your basement, and you've instantly lost a chunk of that energy. So you lost a chunk of that energy up and out the chimney through combustion. You lost another chunk of that energy through, say, jacket losses of the heating system. But nonetheless, with any traditional fossil fuel-based system, they're never going to be 100% efficient. Because for a 100% efficient, like fossil fuel-based system, it would mean that you're dumping combustion byproducts into the home, and that would more or less instantly kill you and or ruin your house. So like all combustion-based equipment needs to be vented, it needs to be exhausting some of the energy or some of the fuel that you put into it. Additionally, with most combustion-based equipment, they also have a distribution system that they're tied to. So for my home, it originally had a steam distribution system. So what needed to happen is this system down here needed to boil water to create steam, and then it would send hot steam up pipes scattered throughout the home, running through unconditioned spaces until it would get to a radiator. But sometimes during the distribution process, you'd be losing another chunk of energy. So with some fossil fuel-based equipment, when you're looking at the total amount of efficiency of it, you're putting in 1 unit of fuel and you may only be getting half of that energy actually delivered into the home. We'll say like a brand new 97% efficient radiant floor heating system, maybe that's 96% efficient. Okay, so do know with a fossil fuel-based system, they're never going to be greater than 100% efficient. Say with using electricity, so say that I take 1 unit of electricity and I stick that unit into my toaster oven. All of that electricity gets converted into heat. So some of the heat ended up switching bread into toast, but some of that electricity ended up heating up my kitchen, okay? So you put in 1 unit of electricity, it's always going to put out 100% of its output in the form of heat. Electricity is normally expensive because all of the inefficiencies of it happen before you bought that kilowatt hour on your electric bill. With a heat pump system, you put in 1 unit of electricity, and what ends up happening is because it's just using electricity to move energy from one location to another, it typically is generating somewhere between 2.5 to 3 units of heat into the home. So these are all done to scale, but it's just a massive amount of energy or a massive amount of heat that it can be adding into the home. One thing about coefficient of performance with heat pumps, though, is it's not always fixed. So say with the toaster oven, which would have a coefficient of performance of 1, you put in 1 kilowatt hour of electricity, it's always going to put out 3,412 BTUs. Say with a heat pump, when it's warm outside, maybe 1 unit of electricity and nearly 12,000 BTUs worth of heat. But say by the time that it's 5 degrees outside, it may be 1 unit of electricity and just a little over 2 units of heat. And the performance here is reflective of one specific model number. So do you know that there's thousands of different heat pumps on the market, and all of them are going to be performing differently. But with like a well-performing cold climate air source heat pump, typically it's always going to have a coefficient of performance of greater than 2. So it's always 1 unit of electricity and over 2 units of heat out. With how much do heat pumps save? I want to just highlight MassSave has their own heating costs calculator, and what it ends up doing is you punch in your zip code, punch in the square footage, the type of the heating system, how much dollars you're spending, and then you can push calculate savings, and then the output of this will look like something like this, where it will say if you switch over to an air to water heat pump, you'll save 1,500 and you'll be displacing 2.9 metric tons of carbon monoxide. Carbon dioxide, excuse me. So do know that this is a resource. I'm going to highlight some additional resources throughout training, because one thing, say, because we have someone from Concord as well as from Reading Municipal Light Department, the rates that would be shown on this calculator are not reflective whatsoever of what those towns would be paying. Additionally, I don't know if with Sue or Jillian, if either of your towns have clean energy community aggregation programs, but if they do, oftentimes the rates that you worked with through the suppliers is significantly less than what an investor-owned utility would charge. So I'm happy that this tool exists, but this tool is not always reflective of like the wide electrical marketplace in Massachusetts. And then the other thing that this is missing is in Massachusetts, we have some of the best retail net metering policies for on-site renewables. And this completely doesn't address anything about how much electricity their roof is already producing. So it's a calculator. It's something that you should be aware of, but oftentimes it's not always going to be the best resource. So this is how I think of this. And do know that I'm happy to share this calculator with all of you as well, if you do think it'd be helpful to use this as a lens for your own heat pump program. So let me just start off with highlighting the rates that we're looking at on the right-hand side. And let's just highlight as well that I have a heat pump, and the performance data of it is this. So when it's negative 15 degrees outside, this heat pump, 1 unit of electricity, under 2 units of heat, but at 5 degrees, a little over. And when it's 47 degrees outside, 1 unit of electricity and 4.5 units of heat out. So fuel prices fluctuate as well. So they're changing all the time. but these are the rates that I'm using. So I kind of went halfway between like an investor-owned utility and an MLP rate. So I said 30 cents per kilowatt hour. But this is what it looks like. So first things first is on the right-hand side, we have the count of how many hours we spend at each of the different temperatures, and that corresponds with the gray. Okay, so if we're seeing the gray, we would see that over the course of an average year, we spend, say, somewhere around 180 hours at 32 degrees. Okay, and we'll see that as the temperature drops below freezing, we'll see that we end up spending less and less and less and less amount of time at each of those hours, or at each of those degrees, excuse me. And what we have on the left-hand side is how much it would be costing to heat at each of how much it would be costing to heat at each temperature, no matter what fuel you're using. Okay, so I see that the yellow is electric resistance, and I could tell that that is wildly more expensive than anything else, any of the other options. The next thing that we would have is propane, and we would see that propane is wildly more expensive than kind of this bottom group of things. And then the black is home heating oil, and then the blue is what natural gas would be costing. The orange color would be ground source heat pumps, and the green color is air source heat pumps. So one of the things that I could say is that when it is above freezing out and you're heating with an air source heat pump, it's going to be just as cheap as natural gas, a lot cheaper than home heating oil or propane. But as the temperature begins to fall below freezing and the heat pump needs to work harder to extract energy and move it from one location to another, we would see that it does become more expensive than natural gas. And then probably somewhere right around 20 degrees outside, it becomes even more expensive than home heating oil. One of the things that I like this chart is like, yeah, it becomes more expensive than home heating oil. And maybe at 9 degrees, it becomes more expensive at propane. But should we really be too concerned with it when we look at kind of the total number of hours or like the total cost, when there could be real savings over the course of the entire year with just running a air source heat pump system or just running a ground source heat pump system, not needing to be maintaining an additional $10,000 to $15,000 combustion-based appliance. So I like this chart just because I think that it visually kind of gives you a better understanding of what heat pumps cost to run throughout the entire temperature spectrum. And even I also like this chart as well because it acknowledges that sub-zero temperatures are a reality in our region. But there is a question of whether or not we should be designing a heat pump system to be covering that load. Because when you look, it's, they do happen, but the amount of times or the count that we spend at those is next to nothing. So depending on the fuel, depending on the utility price, it could be favorable or unfavorable to be running air source heat pumps compared to other fuels. Where there's kind of no question about it is in terms of, instead of thinking of dollars and cents, we're just thinking about emissions. So if we're just looking at the CO2 equivalents of all of the different fuel options that we would have, we would see that air source heat pumps and ground source heat pumps have significantly less climate impact than fossil fuel-based equipment. The other thing that I like about this chart as well, and why I think that this chart works, is it is also interesting to see that, say, when it's warmer outside, it could even be that an air source heat pump is more efficient than a ground source heat pump, because if the air temperature is 55 degrees outside, the air source heat pump is going to be more efficient than a geothermal heat pump where it's trying to pull energy out of 45-degree ground. So I do like this little crossover point happening, and it did kind of confirm that this chart makes a lot of sense. All right, we'll talk a little bit about system design and cost in a bit more detail, but high level, anytime that I'm thinking about a ductless mini split, like something on my wall or something on my floor, I would be thinking that is going to cost somewhere around $5,000. So say you want 8 ductless mini splits, I'm instantly thinking that that type of a project is a $40,000 project. Say that you think that you can get by with 8 ductless mini split per floor, and it's a 2-story home, I'm thinking that it's a $10,000 project. Okay. Say if someone's wanting a ducted heat pump system. So this would be to replace their central AC or to replace their furnace. I'm thinking that that type of a project is going to be a $15,000 to $20,000 project. And say that someone doesn't have any duct work and wants to install a ducted system, I would be thinking that's a $20,000 to a $25,000 project per floor. Okay, so say you have a colonial style home and you want to have a heat pump system down in the basement, another heat pump system up in the attic. I would be setting expectations that that's likely a $40,000 or a $50,000 project. At the same time, I'm very much aware that that project could also be a $10,000 project with a ductless unit per floor. And it's going to, you could be sizing that to be meeting 100% of the building's heat load, but there's likely going to be a significantly greater chance of comfort issues throughout the house. Okay, so even with
Wait, sorry, could you, what would cause the more issues of comfort? Could you say that again?
Yeah, so say just having 2 ductless pieces of equipment versus 2 ducted pieces of equipment.
With which one being better?
The more comfortable one would be having 2 ducted heat pump systems versus say 2 ductless heat pump systems. Maybe, hold on, give me 1 second here. Let me just, let's go and we'll push stop for a second. And I'll switch this over. Okay, so also, I do apologize. I don't have good penmanship. Okay, but let's just say that here's a first floor and let's just say here's a second floor. Okay, so you could have, say on the first floor, you could have a ducted system going down in the basement and you have a register here, 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 and then you have a central return in the middle of the house. And what's going to happen in the winter time is this is blowing out air, 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 and this is sucking the air back in and it's being reheated and it's being redistributed again and again and again. And putting in something like this is going to be somewhere between $20,000 to $25,000. Alternatively, you could have had the same exact floor plan. Okay. So I'll just say that this area is like the, I don't know, the kitchen, dining room, over here's the den, and over here, say the family room. You could maybe just put a single ductless unit right here blowing out this way. Okay, and this project could be $5,000. This ducted system over here could be a 24,000 BTU system. And this one ductless unit over here could also be a 24,000 BTU system. So same amount of heating capacity in both of these homes, but one project cost 4 to 5x what this one would have. I drew a favorable floor plan where like, whoa, this one ductless system is completely covering the kitchen and dining room area and blowing freely into the den and the family room. This is not going to have much comfort issues. But oftentimes, like interior design's real, architecture's real, there's a good chance that this one ductless system is not actually going to do an effective job blowing across the home into the other sections. So with ductless, some installers may be like, all right, let's put another ductless unit over here in the den. And now it's going to be a $10,000 project. And then maybe someone else is like, well, I do want one in the family room as well. Now it's a $15,000 project. And instead of having like one big 24,000 BTU system, now there would be, say, there would be one 9,000 BTU system and say like or maybe two 9,000 BTU systems and one 6,000 BTU system. So like there's a lot of potential flexibility with design and budget and comfort that go into like heat pump equipment selection, design, homeowners goals, the rest.
Well, and you're also sacrificing efficiency because of duct losses, correct? And you might lose some control because of airflow in the ducted system.
Yeah, well, so well, first off, hi Nicole. I didn't know that you made it.
Hi, sorry. Oh, I've been here for a bit.
Oh, okay. Sorry about that. So one thing that I will just touch on is, and we'll talk a little bit more about duct design and efficiencies and inefficiencies and cycling and short cycling. But typically with ducted heat pump systems, the performance is a lot better than ductless for a few reasons. Like the main reason is going to be this. So there's one piece of indoor equipment that's going to be, say, triggering the outdoor unit versus, say, having 3 or 4 pieces of equipment. So oftentimes when you're designing with ductless and multi-zones, there's a lot of kind of like inefficiency with one zone calling for a little bit of heat and it's turning on a really big outdoor system. The things that we don't know about with this case is, in my hypothetical, we're talking about installing a brand new ducted system. And just for, say, code minimum sake, everything needs to be sealed and everything needs to be insulated. So in 2023, there's never been more tight air handlers and more well-insulated ducts. So usually, and also if it's going in a basement, it's somewhat of a buffered space, so there's less of a penalty than it being up in an attic. But there's like so many little variables on like homeowners goals, performance goals, whether or not like lots of people that you talk to are kind of interested in these things for air conditioning and they just want to know that it works and doesn't really care about like the very best performance. But I think, you know, the more we're big into energy monitoring at Abode, and like kind of the more performance data that we see makes us feel better about typically recommending ducted systems over ductless systems in terms of performance. But whether or not the better performance is ever going to justify spending 2x more on potentially install, that's kind of like something that is hard for us to answer. And then just the other trickiness is, it's like if you are purchasing a ducted heat pump system, do know that you are purchasing a brand new distribution system for the home that is likely not just tied to this current heat pump. So when you're putting in, say you're spending $25,000, 5,000 of that is going, 5 to 10,000 of that is an investment in your current heat pump, but your next heat pump and your next heat pump after that. So there is a little bit of that also needs to be kind of evaluated.
Yeah, it's apples and oranges if you're trying to compare it directly. Yeah.
Yeah. So like with my own, I ended up going with ductless because I had architectural interior design complexity, architectural complexity, but there is something that feels a little sad that I spent $20,000 on, a little over $20,000 on a heat pump system, and like 15 to 20 years from now, like everything's going into the not trash, but hopefully recycled, versus with a ducted system where it's like you spend a little bit more money, but it's like, yeah, it's just the air handler as well as the outdoor unit that's getting changed up. So, okay. So I'm just gonna briefly touch on this last part, and I'll say that we'll cover more about electrical capacity throughout training. But do know that for a lot of homes that say had natural gas, they may only have, say, 60 or 100 amp service because they were using gas for their cooking, they're using gas for their domestic hot water, gas for their for drying their clothes. So oftentimes with homes that are older that had natural gas, they may have limited electrical service that could make adopting air source heat pumps exceed the available space on their main electrical panel and exceed the capacity of the wires coming in from the street. So for some people to adopt air source heat pumps, they need to upgrade their electrical service, and doing so typically comes in somewhere around $3,000 to $6,000 is typically what I see those coming in at. Oftentimes upgrading electrical service is beneficial because, going back to something that I said before, we need to electrify everything. So they may be doing it for their air source heat pump, but they'll find additional benefits when they do get their new EV, that they could be putting in a 50 amp level 2 EV charger that will charge their car to 80% over 2 hours versus having it plugged in with a 110 volt outlet where it may take over 24 hours to charge their car. So there is additional benefits of having more electrical service and not less, but sometimes that's really big bucks that is required to make that happen. So just some key considerations. So before upgrading a heating system, just make sure that the house is as buttoned up as possible. And if it's not implemented, size the heat pump system for the changes that will be happening while you're in ownership of the home. So if you're planning on replacing all your windows in the next 2 or 3 years, I would size the heat pump system to reflect that if you have an existing heating system that's in place. So there's no reason to be oversizing the heat pump system for the house as is versus where you're planning on getting the house to be. We'll talk more about integrating with a pre-existing heating system, but the only times that I really think that this makes a lot of sense if someone is very much concerned about polar vortexes, which, as we learned from probably 4 weekends ago or 5 weekends ago, are real here. And then with electrical usage, just know that if your heating expenditures with home heating oil is like $3,000 a year, do know that your electric bill is probably also going to be somewhere around $2,000 to $3,000 more over the course of the year. Or say if your gas expenditures were $2,000, it could be that your electrical expenditures are now going to be $2,500 or $3,000 more per year. But it all depends on where you're getting electricity from, as well as what the commodity price was of what you were previously paying is. Okay. So we're now just going to cover some of the air source heat pump equipment options and what a likely path could look like for upgrading. So say that you do have an existing furnace, a fossil fuel based furnace. It's likely going to be a pretty darn easy switch with ripping out that furnace and putting in a whole home air source heat pump system. Alternatively, you could just be putting in an air source heat pump system that sits on top of your fossil fuel fired furnace. So there's 2 different options. There's one with just changing the air handler, and then there's another option where it's adding a heat pump directly on top of the existing equipment. And which path the homeowner should be choosing is likely going to mostly be dictated by what the heat load is of the home. So say, for example, that the load of the home is 70,000 BTUs per hour. The biggest heat pump system for residential is around 50,000 BTUs per hour. So that person would likely need to put a heat pump on top of their fossil fuel fired system. But say if the load of the home was 30,000 BTUs per hour, I think that it's often goofy to be putting a heat pump on top of the furnace when a whole home heat pump system could be meeting 100% of the building's heat load. Say if you start off with a boiler, so a furnace heats hot air that goes through vents, a boiler heats hot water or makes steam that goes through radiators or baseboards. And if you have that, it's oftentimes more sensible to just be designing with ductless mini splits like I did in my own home. Say if you have a central AC, it's somewhat of a no-brainer to switch your central AC into a heat pump, because now out of that distribution system, now you can do both cooling as well as heating. And on the cooling side, the performance of heat pumps is typically a lot more favorable than, say, an old single stage central AC. And what I mean by favorable would be lower operating cost and an increased comfort, because the equipment can modulate to match the load of the home. And when it's modulating and matching the load of the home, it oftentimes does a much better job of removing humidity from the home as well. All right, so as far as ductless equipment goes, there's a few different types. So there's wall-mounted units, floor-mounted units, and ceiling-mounted units. A few nuances with each. Wall mounts are the most popular, and they typically have the best performance for a few reasons. One, all the latest and greatest features typically make their way into the wall-mounted units first. Two, there's nothing that could be obstructing their airflow. So it doesn't, it typically gets around couches and sofas just because it's high up on the wall. Floor-mounted units I like a lot because you can drop the line sets down through the basement and then out the house. So architecture is real and it matters. And sometimes having like line hide materials running all around the outside of the house could be problematic when it's connecting these wall-mounted units. So floor-mounted units can look a bit more elegant. And this is not an issue for me right now with like mobility, but at some point in my life, it could be risky for me to be getting up on a step ladder or getting up on a chair for changing the air filters. So I do really like the floor mounted units just because, you don't have, you can get the filter without setting up a ladder. It's like, that's nice. And as far as filters, we won't talk too much about it, but the filters typically for most homes just need to be changed or cleaned once per season. So between summer and winter, between running the system in heating mode and cooling mode, you should be cleaning the filter. And then lastly, with ceiling cassettes, most of them are 22 by 22, so 22 inches wide by 22 inches long. And that's tricky because most of our framing in New England is every 16 inches, there's a framing member, so a floor joist. So here's a floor joist, 16 inches later, there's another floor joist, 16 inches later, there's another floor joist. So when this equipment's 22 inches wide, it means that it won't fit without a carpentry project. And for some towns, cutting away a floor joist means getting a structural engineer to sign off on it. So it's very rare in retrofit environments seeing ceiling cassettes being installed. Some manufacturers have units that will fit within 16 inches on center, but I rarely ever see them being proposed. Okay, so in addition to ductless equipment, there's also ducted heat pumps. And for ducted heat pumps, there's really three different ones. There's little ones, medium ones, and big ones. And as far as what I mean by that is a little one may be sized to do a room, a medium-sized one may be sized to do a zone, potentially an entire floor. And then there's big ones, which would be called the central heat pump, and those would be designed to do an entire floor or an entire home. So do know that ducted heat pumps are a reality, and there's different ones on the market depending on the capacity as well as the length of the ducts that are needing to be run.
Mike, can you go back to
Yep.
the slides, whether you have the ducted versus non-ducted?
This one?
Yeah.
Yep.
So how do you know what will work best if you will need to install a ducted system?
Sorry, your audio was just a little bit choppy.
Oh, sorry. For homes that have ducted systems, can they go to ductless?
Yeah, so sometimes mixing and matching ducted and ductless could certainly make sense. So say if the ductwork is in really bad shape and it's very leaky and it may have asbestos on it, that maybe you don't want to be using that duct distribution system and you're going with wanting to design with ductless. Where I think it makes the most sense to be mixing and matching ducted and ductless is if there's a room that has different thermal characteristics. So a very common thing that we see in Massachusetts is you have a great room above a garage. So the entire home, the main body of the home is above a basement, and then you have one room with vaulted ceilings above an unconditioned garage. That room is likely going to really benefit from a ductless system because that room is performing wildly differently than the rest of the zone would. Or say you have a Four Seasons room, that could be another example of a room where even if there's existing ductwork, where would really make sense to be putting in a separate ductless unit.
Thank
yeah.
you.
Yeah, and then the other thing too is like, let's just say that you did have, you just had I can't get around the fact that like a ductless unit costs $5,000 and a ducted heat pump costs like $15,000. So if you are always just spending time in like one room of the house, it may make the most sense to just put in a ductless unit there and run it similarly to like a wood stove or a pellet stove, which we'll talk about in just a second here. So just as far as the outside of the home, do know that line sets are going to be part of the installation. So I have two different photos over here. One's my colleague's house and one's my house. But my colleague's install, I think, looks a bit more elegant than mine, which is on the right-hand side. But do know that you can get line hide covers that be potentially matching the siding. Alternatively, you can always be painting line hide covers to match the color of the house. So just be aware that that you're always needing to come up with a way to be connecting the outdoor equipment to indoor equipment. And sometimes this could have a impact on the overall architecture of the home. Other times you're putting it on the side of the house where you already have the electrical connection, the wires coming in from the street, and maybe you don't care. But just be aware that this is real and this is something that homeowners should be talking to their installers about, is how are these line sets going to be run? And is there anything that could be done to be minimizing the impact of it? I would say with my own house, with looking at this photo more, I do wish that he just ran this a little bit over to the right-hand side and ran it straight down, but I think he felt like he was too close to the electrical wires. So that's why they kind of went up over and to the side.
Mike, if we're doing internal construction, does it make sense to put the lines inside a wall that's going to be covered up in sheetrock and painted and finished?
Yeah, most of the time, if you can be running the line sets inside the house, you should be running them inside the house. Just know that one thing that I didn't talk about is condensate. So when these systems are running as an AC, one of the byproducts of running it is moisture, and that does need to get drained out. So it's easier to drain out the moisture on the outside of the house than draining it out down in the basement if there's not already a laundry or a sink down there. So sometimes that could be that could just require a little bit of extra attention to detail. It's just making sure that there's a solution for getting all the condensate out. But yeah, there's nothing wrong whatsoever with running the line sets inside the house. And say, even with a ducted heat pump system, oftentimes one of the things that they could be doing with getting up into the attic is they could oftentimes be using like an old chimney chase to be running the line sets up. So there'd be no visible line sets from the outside, which is, well, no visible line sets other than the small connection between the outdoor unit straight into the house.
So my question was specifically about burying the lines inside a wall that's going to be closed up and finished. Is there a concern about needing to maintain them at some point in the future?
No, not really. It's a pipe in a copper tube, really, more or less. So there's nothing wrong with burying them, and they could also be installing, say, like a PVC pipe to be using as a conduit. So say for future installs as well, that they're able to kind of freely pull the lines through.
Thank you.
Yep. As far as outdoor equipment goes, do know that every manufacturer has different sizes of outdoor equipment, and the smallest size outdoor piece of equipment is like 6,000 BTUs, and the largest piece of outdoor equipment is like 60,000 BTUs. So some equipment is quite small and others is quite large. And just to kind of gut check this as well, so we don't use rules of thumb with sizing heat pump equipment, but just if it's helpful to get an idea of this, most homes in Massachusetts probably need somewhere around like 25-ish BTUs per square foot. So say if a house is 2,000 square feet, they're going to need 50,000 BTUs worth of like heating capacity. So with knowing that, say, some homes need 50,000 BTUs worth of heating capacity, a 6,000 BTU system is where the mini of ductless mini split comes from. It's just picking up a small bit of the load. However, over time, these equipment has gotten more popular and the sizing has kept going up. And that's how we now have, say, like a 60,000 BTU piece of equipment or a 48,000 BTU piece of equipment. So going back to sizing for single zones, most of these are somewhere between 6,000 and 24,000 BTUs. Most of the time you have a single zone, it's around that capacity. With multi-zones, where it's, say, one outdoor unit and it's doing, say, 2 or 3 indoor units, these are usually somewhere around 18 all the way up to around 36,000 BTUs, okay? And what would happen over here is you'd have a line set from this ductless mini split over to here, and then a line set for each of these ducted mini splits over to here. When you're dealing with like very big pieces of equipment, like 36,000 BTUs and greater, now, instead of it looking like one of these outdoor units, it looks like 2 of them stacked on top of each other. And these could be handling up to 8 indoor units. And instead of the lines all connecting back to the outdoor system, they would be connected to what's called a manifold or a branch box. And that equipment would typically be installed in the basement or the attic. So the indoor units run to the branch box, and then the branch box runs to the outdoor system, and it just kind of really cleans up the line sets. But they perform a little bit differently, and we'll talk about that a little bit more in training. But just know that with outdoor equipment, there's a lot of variability in them. I oftentimes think I should be renaming some of these headers on this slide. but I'm going to rename this and I'm going to call this the efficiency main approach to heat pumps. So the efficiency main approach of heat pumps, which is Maine has had more heat pump adoption than anywhere else in the country, would be this. You put in one system, a ductless unit, and you run it the same way you would a wood stove or a pellet stove. And what I mean by that is the room that it's in is going to be hot or it's going to be warm. And then the further away from the unit that you get, it's going to become colder and maybe it could even become uncomfortable. But this is a perfectly fine approach if you want to have, say, the lowest install cost and you're okay with temperature deltas throughout the home, which I think in, say, a region like Maine, where a lot of people are very accustomed to wood heat, is not that big of an issue. But say in Massachusetts, where more people, I guess, are familiar with or expecting, say, central heating systems and central distribution systems, and every room being probably within like a 1 to 2 degree delta of the next room over, this may be a little bit risky in terms of comfort. So do know that you could have a heat load for this zone of 18,000 BTUs per hour. You can put in an 18,000 BTU per hour ductless mini split, and you set this thing to 72 degrees or 74 degrees. And hopefully this bedroom on the back corner is 68 degrees, and maybe this bedroom down here is 65 degrees. If someone is trying to take this approach, I do always recommend that they install a wired or a wireless thermostat to go along with this equipment. And the reason for that is if the thermostat is, say, in this bedroom and you set it to 68 degrees, this piece of equipment is going to keep running as hard as it needs to until this bedroom is 68 degrees. Without a wired or a wireless thermostat attached to it, if you just, hold on 1 second. If you're just controlling the unit with, say, like a handheld remote, all this does is it says to the unit, like, do an algorithm inside of you until it's 70 degrees. But that algorithm inside of the unit doesn't know that, say, this bedroom is 65 degrees. So it just kind of helps guarantee that the space that you're trying to condition actually gets to that temperature before the unit tries to short cycle.
Is the temperature sensor in the remote or in the unit?
The temperature sensor's in the unit and not the remote.
So you couldn't take the remote to the bedroom and let it be the remote thermostat.
Yeah, so LG has a remote, okay, and there's a thermostat button on it, and you push the button and it says the temperature at the remote, but there's no actual communication for this to like send a wireless signal over there to increase the temperature to where this device is. So you do need, say, a separate thermostat. In some manufacturers, instead of having an actual thermostat, they have these little like puck kind of dongles that you can put in the room that you want to in the room that you want to do the temperature sensing, and then you'd be using your phone in their app to say, I want that room to be 70 degrees. And then that tells what the ductless unit to be, how hard it should be working.
Thank you.
Yeah, and in full transparency, I very much wish that all of the handheld remotes were wireless thermostats. And I think that would solve a lot of user error or user confusion, or just the non-intuitiveness of the ductless equipment and the controls of it. So that's why I'm telling you that the best approach would just be, if you are trying to design like this with just one ductless unit per zone, that people really should be thinking about getting a thermostat from their manufacturer, and most of the thermostats are all wireless. So it does add about $300 to the project, but the overall comfort is a lot better. And it's slightly more elegant too. I think just in America, we're just familiar with going to something on the wall to be controlling the heat versus controlling the heat the same way that we would a television set. We'll talk more about this concept throughout training, but here's the core concept over here. It's really easy to oversize a heat pump system when you're trying to go pretty much put a ductless unit anywhere that you would have originally had a radiator or a register. And why this is a problem is because with heat pumps, they modulate, but they only modulate so much. So for this example, we have 4 ductless pieces of equipment. The smallest outdoor unit that supports 4 ductless units from a major manufacturer is 36,000 BTUs per hour. As I said before, over here with this example, we have an 18,000 BTU load and an 18,000 BTU ductless system. The smallest piece of multi-zone equipment from a major manufacturer is 36,000 BTUs per hour. And that piece of equipment only modulates down to 22,000 BTUs per hour. So what could happen if you want to put, say, a ductless unit everywhere where you had a register in each and every room, is it is going to be oversized for the home, even when it's running at its lowest or even when it's running at its minimum capacity. And that means instead of having a coefficient of performance closer to 3, it'd be closer to 2. So it has a big impact on performance and can also have a big impact on its ability to remove moisture. So going back to the example of not using a rule of thumb and saying most homes need around 25 BTUs per square foot, say if a bedroom is 150 square feet, so just like a small bedroom, that would mean that that bedroom needs 7,500 BTUs per hour at 5 degrees or at kind of the coldest temperature that we'd experience over the year. The smallest ductless mini split is 6,000 BTUs per hour. So it'd be oversized still on the coldest day of the year. And then it's wildly oversized on every time else in the year. So do know that with ductless, oversizing can become very easy to do when you're just trying to put in one unit everywhere that you had a register or a radiator. What we try to encourage contractors as well as homeowners always to do is properly size the system. So just figure out what the load is and size it accordingly. So say that the load is still 18,000 BTUs for the house, you could have a 9,000 BTU ductless unit over here and a 9,000 BTU ducted system over here. And with the ducted system, it could have, say, 3 registers, 1 in each of the rooms, and the ductless system would be picking up this whole area. And now there would be a zone for the one wing of the house and a zone for the other wing of the house. And that could be beneficial because the sun moves around throughout the day. So sometimes the left side and the right side are have different external loads on it. So it's cool when the equipment can match those two. But there would also be nothing wrong with this house with just putting in one big ducted system down in the basement and then putting registers throughout. So that could be another real approach for also right sizing it. And then the last approach for right sizing, it could be that they could just be putting in a 9,000 BTU ductless systems in one of the bedrooms. And then they can be doing things like a pass-through vent, or they've just become accustomed to the fact that they'd have one bedroom that's slightly more climate controlled and another bedroom where they're relying more heavily on the thermal envelope being real. but I can say, like, I love my children dearly, and neither of them have the ductless mini split in their rooms, and they are perfectly fine. So you really don't need a ductless unit in each and every room, as long as you're sizing the equipment to meet 100% of the building's heat load, and that there's no catastrophic thermal envelope issues. So what I mean by that would be like, say if a room is above a crawl space, or say that a room jets out and there's exposure on 3 sides, or there's a room with an excessive amount of glass or glazing, like all of those spaces would be really risky not to put a ductless head in. But as long as the room is like performing like a regular room, there's no reason to believe that one room will be 70 degrees and the room right next to it without the ductless unit is going to be 60 degrees. Like if that room is a 10-degree difference, it's like there's something wrong with the thermal envelope of the home. All right, I'm gonna skip over geothermal. Hold on, let me just, yeah, let's, I won't skip over geothermal, and we'll talk about rebates on the next section. So with geothermal, geothermal is also called a ground source heat pump, but most people refer to it as geothermal, or they'll just call it geo. And do know with geothermal that it's going to also have multiple components, just like an air source heat pump does. So there's always going to be an outdoor component, which is going to be more or less earthwork or site work. So there's a vertical loop and sometimes multiple vertical loops, depending on the load of the home. So a vertical loop would be the same application as putting in a well on your home, where they're boring down into the ground and then they're running a pipe or pipes down into it that would be pulling energy from below grade and bringing that energy into the home. And sometimes with vertical loops, they're closed. And other times with vertical loops, they're actually pulling up groundwater, stealing the heat off of it, and then depositing the groundwater back into the ground. So there's 2 different types. There's also a horizontal loop, and that would involve getting an excavator and digging trenches throughout your yard, and then it'd be putting in pipe that way. There's also indoor components, and that would be the indoor heat pump, and there's different types. So there's some that steal the energy off of the groundwater and it puts that into air, and then there's others that steal the energy off of the groundwater and it puts it into a low temperature hydronic distribution system, which we'll talk about in a minute. And then there's other ones that can do both. And then for the distribution system, that is, how is that energy going from the heat pump in your basement or in your utility closet throughout the home? So that could be through ductwork, low temperature hydronics, or things that look just like a ductless mini split. When we're thinking about the efficiency of, say, like a ground source heat pump over an air source heat pump, it really is this. Is if you want your house 70 degrees, the heat pump is going to need to work a lot less hard if it's pulling heat from, say, the ground, which is 45 or 50 degrees, than the outside air, which could be at 15 degrees or 0 degrees or at 40 degrees. Like, there's going to be more energy or more work that's going to need to happen to pull heat out of the outdoor air than the ground throughout the vast majority of the heating season. Therefore, instead of a heat pump running somewhere at a coefficient of performance of like 2.5 to 3, it has a much greater likelihood of running somewhere between 3 all the way up to a coefficient of 5 over the course of the heating season. So ground source has a real big potential to become much more efficient in wintertime heating. And then in the summertime, it's an even more favorable narrative, because below grade it's already cooler than what most people would ever want their home to be in the summertime. So in the summertime, geothermal systems have very little work to do to be able to remove the heat and remove the moisture from your home, because it really is just dumping all of that energy right underground. For geothermal systems, they're incentivized with a 30% federal tax credit, and that helps a ton in terms of affordability. There's also in Massachusetts this alternative energy certificate program that's somewhat broken, but those rebates are also available for geothermal customers. Mass Save is a $15,000 whole home heat pump rebate for geo. You can use the heat loan and there's no sales tax on any of that equipment. So for some projects, this 30% federal tax credit goes a really long way in making it affordable. But the big thing with geothermal systems is oftentimes, for a lot of people who are doing this, you're needing to pretty much buy all three components. And because of that, most geothermal projects start somewhere around $60,000, and then they kind of really go up from there. So there's plenty of homes where I've seen proposals where the HVAC contractor is looking for around $100,000 for doing this. But one good thing with it, and just thinking of investments, the outdoor loop lasts 100 years. So that's not going anywhere. And the distribution system, if someone's putting in brand new ductwork or putting in low temperature hydronic emitters, those are going to be lasting 50 or 100 years. So sometimes the price tag is really scary, but it really is a long-term investment for the home. The next thing that I'll talk about is air-to-water heat pumps, which is a real technology and it's an emerging technology. And I think that more and more contractors are becoming familiar with it and are somewhat looking forward to their first air-to-water heat pump project. So let's just go over a few things. So comfortable, zonal, fully distributed, quiet. So what I mean with all of these things is no one except in high-end homes is putting in radiators anymore or baseboards anymore or radiant floors. Like that product category in some ways has moved into a more premium building for new construction. And the reasons for this is it's a lot more expensive to be doing hydronics than it is to just be building ductwork and dumping air throughout the home. So with air-to-water heat pumps, it is kind of considered a more premium version of heating. Some other benefits with air-to-water is you can be doing domestic hot water, and domestic hot water is the hot water that's coming out of like your sinks and your showers, okay? So with all of the heat pumps that we've talked about before, there's no solution for it with that kind of split outdoor unit that's heating and cooling the home to do anything with your domestic hot water. So for that, it's always a different type of a heat pump system, or you're thinking of another technology like solar thermal. With air-to-water heat pumps, they can do cooling, but it's a lot harder than air-to-air heat pumps. The big thing about this and why these are not everywhere is because the temperature that these put out isn't 180 degrees like your baseboards may be looking for, and it's not 212 degrees like your steam radiators may be looking for. At its highest is around 140 degrees, but even 140 degree water isn't leading to the best performance of this equipment. The best performance is somewhere around like 90 to 120 degree water. So what this means is for the vast majority of homes, you can't rip out your boiler and put in an air-to-water heat pump system. Now, one thing that I will say about all of this is steam came around and then people are like, and then forced hot water came around. And plumbers 100 years ago could go look at a steam radiator and then they could do the math, and then they could say, yes, we could convert this radiator that was designed to provide 212 degree steam into something that could safely heat the room with 180 degree water. So 100 years ago, plumbers were already figuring out whether or not, say, changing a system from steam to forced hot water was safe. It's likely in the near future that more contractors could be looking at someone's existing baseboards, figuring out what the load of the home is, and confirm whether or not that they could be thinking about switching over to an air to water heat pump with a much lower water temperature flowing through those baseboards. And even if the answer is no, that this home may become too cold, air to water heat pumps could certainly be supplemented with air to air heat pumps. So you could have 120 degree water flowing through all your baseboards, and you could have a ductless mini split upstairs, a ductless mini split downstairs to do your cooling, as well as to supplement the air to water heat pump. So right now with air to water heat pumps, there's a real challenge for the vast majority of homes, but it's not impossible. I want to just highlight the components of this, and there are different types out there, but this is typically what most installs look like. There's a system outside. Oops, sorry, something weird happened with the graphic. There's a system outside, and the system outside could be small with like one fan, or it could be big with two fans. This system outside goes to something that looks like a hot water heater cylinder inside. And what's going to be happening over here is water with a glycol or antifreeze solution is going straight from this thermal storage tank to the heat pump to be heated or to be chilled. Then when you're calling for heat inside the home, say that you have radiant floors, which already want to be around 90 degrees, the radiant floor zone would call, and then through a circulator pump, energy inside of this thermal storage tank would flow into these radiant floors, okay? And so if 90 degree water came in, then say 75 degree water came out, and that 75 degree water goes back into this thermal storage tank to get reheated again by this air to water heat pump system. In addition to being able to power radiant floors, it could also be used to power, say, like low temperature baseboards, which is what, if you've been to Europe before, everyone uses over there. And this is also kind of crept into more kind of higher end American homes as well. Additionally, some of you may be familiar with the term hydro air, where instead of having a combustion-based furnace, what there would be hot water coils inside of the air handler, and then air from the home would pass over those hydronic coils and heat the air that way. So these are kind of the different types of distribution or the different types of emitters that are compatible with air to water heat pump systems. Any questions about air to water heat pump systems? So we're what's funny is with the last class, I'm like, oh, I finally got really good with time management. I didn't go over on any of them, but I realized that maybe that people weren't just asking as many good questions. So we're up on time. So as far as my next steps to do is, we will cover on the next section. On the next session, we'll cover rebates, resources, tax credits, and we'll kind of just pick right up where we left off. I will be sending a follow-up email that will have the link to office hours. So if you ever want to schedule some one-on-one time, you'll be good to go with that. But I'm excited to be working with you guys in the coming weeks. And I don't have a hard stop right at 12, so I'm more than happy to stay on and answer any additional questions as well. But thank you everyone for attending. And yeah, I am really looking forward to working with you in the coming weeks and months.
Well, thank you, Mike. This is really informative. Is the slide deck available to us?
Yeah, in the learning management system or the self-paced learning, the slide deck is there. There may be a few tweaks with the one that I presented today and what is currently uploaded on there. I'm always tinkering, but yeah, you should be able to view the deck and download it as well for internal resource.
Thank you.